Hello everyone, this is MD Atiqur Rahman. I am a PhD candidate in the School of Electrical Engineering and Computer Science at the University of Ottawa under the supervision of Professor Robert Lagunier. So I am going to present our paper titled Single Stage End-to-End Temporal Activity Detection in Untrimmed Video. So here is an outline of this presentation. First, I will quickly go through the introduction and recent works, followed by the motivation of this work. After that, I will discuss our proposed approach, followed by experiments and results. So we address the problem called temporal activity detection in this paper. The goal of temporal activity detection is to temporally localize each activity happening in a temporally untrimmed video and also to classify those activities. To better understand what this task actually involves, let's have a look at this example video. So this is a video of a basketball game where the players are doing some activities called basketball dunk. So as you can see here, there are multiple basketball dunk activities going on in this video. The video is long and temporally untrimmed, meaning that the activities are buried under temporally cluttered background. So the task here is to find out exactly when an activity starts, when it ends, and also to classify the type of the activity. So as per the recent works, since there is a close resemblance between object detection and the temporal activity detection, the recent approaches to temporal activity detection have been directly inspired by the advances in object detection and are broadly categorized into two-stage approach and single-stage approach. The two-stage approaches basically follow the leading two-stage object detector called first CNN and operate in two separate stages. In the first stage, the algorithms generate the activity proposals, while in the second stage, these proposals are classified into specific activity categories, and the activity temporal bounds are also further fine-tuned. The single-stage approaches, on the other hand, basically follow the leading single-stage object detector called SSD and try to combine these two separate stages into a single stage, and therefore run significantly faster than their two-stage counterparts. So therefore, in this paper, we are interested in the single-stage approach. However, the existing single-stage methods for temporal activity detection do not learn the spatiotemporal feature representations of a video in an end-to-end manner. Rather, extract deep features from pre-trained 2D or 3D CNNs, followed by complex feature aggregation methods to provide the temporal modeling. Since these 2D or 3D CNNs are specifically optimized for image or video classification tasks, such off-the-shelf features may not be suitable in a diverse video domain for the temporal activity detection task. We therefore attempt to fill in this gap by proposing a single-stage end-to-end trainable framework for temporal activity detection. So we closely follow the single-stage object detector called SSD. Therefore, before I start explaining our proposed approach, let's have a closer look at the SSD architecture. So as you can see here, SSD basically uses a 2D CNN feature extractor, for example VGGNet, to create a spatial feature map. As you can see here, this spatial feature map is further progressively downsampled in the spatial resolution to generate some additional feature maps. So each of these feature maps is basically responsible for capturing objects at different temporal scales. So predictions are made on each of these feature maps and these predictions are combined to train the whole network end to end. So if we take a closer look at a specific feature map, we can see here that the SSD basically employs a set of default bounding boxes at each spatial location on a feature map. So these bounding boxes basically differ in scale and aspect ratios to cover different orientations of objects and scales. So for each default bounding box, SSD predicts the probability of the bounding box to contain an object of a specific category and also predict the box offsets such as the center X, center Y, width and height offsets of the box. So analogous to SSD, we use a 3D CNN feature extractor called S3DG that adopts a two-stream architecture, a spatial stream to capture the appearance information of the video from RGB clip and a temporal stream to capture the motion information of the video from flow clip. The 3D CNN feature extractor basically downsamples the RGB clip and the motion the flow clip in both spatial and temporal dimensions to produce two base feature maps, as you can see here, one for appearance and the other for motion. We use these two base feature maps and pass them through average pooling layer to completely collapse the spatial dimension to produce two temporal only feature maps, as you can see here, one for appearance and the other for motion. We further pass these two temporal only feature maps through 1D convolutions of kernel size 3 and stride 1 to further extend their receptive fields. After that, we add some additional temporal only feature maps with decreasing temporal resolution by using 1D convolutions with kernel size 3 and strides 2, with a view to capturing activities at different temporal scales, just like SSD. Finally, we add apparition layers on each feature map, both for the appearance stream and the motion stream. So just like SSD, we also associate a set of default temporal segments with each temporal location on each feature map in the appearance stream and the motion stream. Finally, the predictions from both streams are combined together using element-wise averaging, which are then passed through non-maximum suppression to produce the final predictions. So this is the whole architecture that we propose in this paper for end-to-end temporal activity detection. Regarding the data sets, we used a highly challenging data set for temporal activity detection called Thumos 14. This dataset contains videos from 20 different sports activities. There are 200 validation videos that are all temporally untrimmed, and we perform training on these validation videos following the standard practice on this dataset, and we report results on 210 test videos which are also temporally untrimmed. So the length of each clip, the RGB and flow clips, is set to 512 frames, following the fact that 99% of the activities in the Thumos 14 dataset have lengths of 512 frames or less. Again, during training, we generate the clips by having an overlap between neighboring clips by 75%, and this is done to handle the activities that start at the end of a clip, and also to increase the amount of training data. But during testing, we limit the overlapping to 50% to increase the processing speed. So here are some results on end-to-end feature learning. This table reports results on 3 different training configurations. The leftmost column reports results when you do not train the feature extractor 3D CNN at all. We just simply extract features and then pass them through the detection architecture. The middle column reports results when we train the last convolution layer of the feature extractor 3D CNN, whereas the last column reports results when you train the last 2 convolution layers of the 3D CNN. So as you can see here, there is a gradual increase in performance as we train more layers in the feature extractor 3D CNN, which supports our which validates our design choice for end-to-end feature learning, which is not possible with the existing state-of-the-art end-to-end existing state-of-the-art single assist methods, because they don't allow end-to-end feature learning. So this, it can be noted here that we did not find any further performance improvement by training more layers of the feature extractor 3D CNN. This can be explained by the fact that the amount of training data in the Thumos 14 dataset is not sufficient enough to train a deep 3D CNN just like the one we used in our work. Similar behavior was also experienced and reported in an earlier paper that we cite in our paper here. So this table reports results on the temporal activity detection task for all the 2-stage and single-stage state-of-the-art methods, as well as our proposed method. So we can see that our proposed method performs for almost for most of the temporal IO thresholds. Of particular interest is the temporal IO threshold 0.5, which is basically used for evaluation, where our proposed method sets a new state-of-the-art by pushing the existing state-of-the-art called decouple SSD by a significant margin, as you can see here. And here we report results on the quality of our proposed activity segments. So on the left, we plot average recall against average number of proposals generated per video by our proposed method and some other state-of-the-art methods. So as you can see, our proposed method marked in green outperforms the other methods for low number of average number of proposals generated per video, which signifies that the top predictions of our proposed method are more likely to contain activity proposals. And on the right, we plot recall for the top 100 predictions against the higher temporal IO thresholds ranging from 0.5 to 1 to explain the boundary quality of the for activity proposals. And we see that our proposed method outperforms other methods for most of the higher temporal IO thresholds. And here are some qualitative results. We visualize results on 2 different test videos. The top one is showing results on the basketball dunk activity, while the bottom one is showing results on the javelin throw. So we can see that our proposed approach is qualitatively doing better on shorter activities like the basketball dunk activity, as well as the longer activities like javelin throw. So that's all, and thank you very much.